Hello everyone, this is Mike Dowding with the SD Minds Physics Department. And this video, I haven't assigned it to any particular chapter, but the material in this video would be appropriate to some of the topics in chapters 28 and 29 as they refer to how we're going to evaluate cross products. And at this point, you might be thinking, well, when it comes to a cross product and I have two vectors A and B, the easiest way to evaluate that cross product is to take the magnitude of each vector times the sine of the angle between the two vectors. And so if I had vector A, which was 5 meters at 30 degrees with respect to the positive x-axis, and vector B was 8 meters at negative 45 degrees with respect to the x-axis, then the way that we could evaluate this cross product would be to take the magnitude of each vector times the sine of the angle that exists between them. And so just a quick sketch here, vector A, vector B. Vector A and vector B would have a combined angle separation of 75 degrees. And so that would have to go into our expression there, and then we could plug all of that into our calculator. 5 times 8 is 40, and then sine of 75 degrees. This would give us an outcome of 38.63. And that's how we're going to evaluate the magnitude of this cross product. However, another thing to remember is that whenever we have a cross product, the result is another vector. So we'll call this vector C. This happens to be the magnitude of vector C. But now we need to know the direction that that vector is pointing. And the one thing that we need to remember about cross products is that the resultant vector will always be perpendicular to the original two vectors that were used, A and B. Now this is not to say that vectors A and B have to be perpendicular to each other. They can, but that's not a requirement. But this is. Whatever direction vector C points in, it has to be perpendicular to both vectors A and B. And for us, the only option is to have vector C pointing either out of the board or into the board, because, oops, that should be vector C. So those are our only two options really, because vector A and vector B both lie on the xy plane, and the only direction that is perpendicular to those would be either into or out of the board. So which one is it? Does vector C have to point into the page or out of the page? And the way that we can figure that out is we need some more information about the vectors themselves. I need to know what directions the vectors are pointing, or more specific, what direction are the components of those vectors pointing. So I'm going to come down here and I'm going to introduce a new set of information. So this is a new pairing of vectors A and B. And we'll just go ahead and make these both three-dimensional vectors. We may as well just jump right in and take care of the fact that vectors can be 1D, 2D, or 3D. We'll just do it all at once. We'll do the 3D case scenario. So vector A, we'll say vector A has components of 3 in the I hat, 5 in the j hat, 8 in the k hat. And if you remember, your I, j, k's are synonymous with the x, y, z directions of your vector. And then we'll plug in some values for our B vector. We'll go with 4 I hat minus 7 j hat and 2 k hat. Alright, so those are the two vectors. If we need some units, we can put those in. Maybe these are position vectors. But now I want to know what happens if I take the cross product of those two vectors. And as we saw above, we can figure out the magnitude of this cross product by finding the magnitude of each vector respectively, and I have the necessary information to do that. I know what the components of vector A are, and back in Physics 1, if you had physics with me, you'll remember the magnitude mantra, square root of the sum of the squares. So we have the square root of the summation of the squares of each component, and we can get a magnitude for A. I'll go ahead and plug these numbers into my calculator. And I'm getting a magnitude that is approximately 9.9 meters. And then we could do the same for vector B. We have 4 squared plus negative 7 squared, 2 squared, and we are going to be squaring negative 7. When we do that, it's going to come out as a positive. We cannot have a negative magnitude, and we cannot have an imaginary magnitude. And so vector B has a magnitude of approximately 8.9. Alright, well, that's not the entirety of the evaluation process. Now we need to know what is the angle relationship between those two vectors. And looking back here, well, the only thing I know is the components of those vectors. And I really don't want to attempt to try and draw these vectors out in 3D space somewhere. I certainly don't want to try to measure the angle between the two of them. That's going to be extremely difficult. And so this is probably not the best approach for trying to evaluate the cross product of these two vectors, at least not in this combination of information. So by having the components of the vectors, is there another way that we can evaluate their cross product? And what we can do is we can say, well, vector A has all of these components, and we're being asked to take the cross product of all of those components against all of the components of vector B. And so what's going to happen here is that the x component of vector A will have to be crossed against every component of vector B. The y component of vector A will have to be crossed against every component of vector B. And then finally, the z component of vector A will have to be crossed against the z component of vector B. So that's a lot of stuff to do, but we can do that. And my preference is to write all of this out in general form. So keep in mind that vector A has its x, y, and z components. Respectively, we know what those values are, but for right now, I'm just going to use the general format. And then for vector B, same approach. We have x, y, and z components, and we know what those components are, so we can plug those in later if we need to. And now comes the part where I need to see what the cross product of each possible component combination is going to be. So we will have a of x crossed with b of x. We will have a of x crossed with b of y. We'll have a of x crossed with b of z. Then we'll have a of y crossed with b of x. We have a of y crossed with b of y. A of y crossed with b of z. And one more time for the AZs, AZ crossed BX, AZ cross BY, AZ cross BZ. So there are 9 combinations here that we need to take a look at. Every one of these is a cross product of our respective variables up top here. But the nice thing about this is that for every one of these cross products, if I plug in the magnitude and angle relationships for every one of these combinations, well, my components are either x, y, or z. And all the x components are going to be at 90-degree angles with respect to the y components and the z components. And all of the x components are either going to be 0 degrees or 180 degrees with respect to any other x components. So I'm always going to know what the angle relationship is between any of these 9 combinations. So let's go for the first one. We have the magnitude of AX, which is 3, times the magnitude of BX, 4, times the sine of the angle between them. Well, AX is in the I-hat direction. BX is also in the I-hat direction. They're both positive. So that means they're both pointing in the same direction, and that means we have an angle of 0 degrees. Sine of 0 is 0. And so that means we don't actually get anything out of that cross product. And that is going to be the case for any cross product that has the same subscripts. So in this case, we had 2 components that were both in the x direction, and like we said, our 2 options for the x direction are either 0 or 180 degrees, but both of those result in a 0. And so that means we will not get any contribution from the AY-BY combination or the AZ-BZ combination. But we should get something from the other 6 combinations on the board. So we'll move over to the AX cross BY combo. We need the magnitude of each times the sine of the angle between them. Well, these are X and Y components, so automatically I know the angle between them has to be 90 degrees. Sine of 90 degrees is 1. And so all that's left is to plug in the magnitudes of the 2 components. We have 3 for the magnitude of AX, and we have -7 for the magnitude of BY. So magnitude -7 is 7. So what we're getting out of this is 21. Now, we have a value of 21, and we know from experience, or at least from what we're told, anytime we take a cross product, we should get another vector. Well, A of X and B of Y are both vectors. They just happen to be in just the X or the Y directions respectively. But they're still vectors, and when we take a cross product, we still have to make a resultant vector. So what direction is this new resultant vector going to point? It has to be perpendicular to the original 2, and like before, we have vectors that lie in either the X or the Y direction, so that means all that's left for our resultant vector is k hat. But are we going to point in the positive or the negative k hat direction? That is the tricky part. So we're going to come back to this 3x3 matrix that we've set up here, and we'll figure out how it is that we're going to evaluate whether or not this should be a positive or a negative k hat direction. So here's how we're going to do that. We have our I hat, j hat, and k hat directions. And IJK, that is alphabetical. And if you can remember your alphabet, you can evaluate your cross products. We'll start with exactly what we had up above. We had AX cross BY. So AX is an X component, that is the I hat direction. BY is a Y component, that is the J hat direction. And as a result, we have to get something in the k hat direction, but is it positive or negative? So here's how we know. If you go with the alphabet, the outcome is positive. Well, what do we mean going with the alphabet? Well, when you recite the alphabet, I comes before J comes before K. So in that case, are we going with the alphabet? Well, I comes before J, and after J comes K. So yep, we're following the alphabet. So the outcome is a positive k hat. Well, what if you go against the alphabet? Well, in that case, you get a negative outcome. So how would you have some combination where you went against the alphabet? Well, let's try this. Let's try j hat cross I hat. What would that equal? Again, we're using I hat and j hat, so all that's left for us is something in the k hat direction, but is it going to be positive or negative? If you go from j to I, is that going with the alphabet or against the alphabet? Well, you're going backwards in the lettering, so that is against the alphabet. And so the outcome is a negative k hat. So we'll just we'll keep track over here of what evaluations we've had so far. And let's try the next combination. Let's try j hat cross k hat. We've already used j and k, so we know that the only option is an I hat for the result, but is it positive or negative? So we'll come back up to our alphabet here. Our alphabet only has 3 letters in it, but we're starting at j hat, and we're going to k hat, so we are in fact following the alphabet, and that means our outcome is going to be a positive. Let's flip the k hat and the j hat around. Now what's happening? Well, we're starting at k hat, and we're going against the alphabet, so we're going backwards in the lettering, which means that we're going to get a negative I hat out of that combination. Alright, now here comes the really interesting one. K hat cross I hat. We've already used I hat and k hat, so we know that j hat is the only possibility. And we've been using this idea of, are we going with or against the alphabet? Well, remember our alphabet is only 3 letters long. I, J, K. And when you learned the alphabet, when you sang the alphabet song, what did you do when you got to the end of the alphabet? Well, as the song says, next time won't you sing with me? So we have to go back to the beginning of the alphabet. Our cross product up here says we're starting with K, and then we go to I hat. Well, how do you get from K to I? We can't go back because that gets us to J. So we have to go all the way back around to the beginning, but that actually follows the alphabet song. So we are in fact going with the alphabet, and the outcome will be positive. And then our last combination would be I hat cross K hat. We've already used I and K, so J is our only possible outcome, but is it positive or negative? Alright, well, we're starting at I hat, and we have to go to K hat. I can't go with the alphabet because that takes me to J. And so I have to go backwards against the alphabet song. And that means I'm going to get a negative J hat as a result. So there are the 6 possible combinations that we can have for the outcomes of cross products using the respective IJK components. You do not have to memorize these because I think it's a pretty straightforward idea that if you can follow the alphabet, you know what your cross product is going to result in. And if you go against the alphabet, you're going to get a negative. Now, one final thing to consider, what happens if one or more of your cross product values has a minus sign associated with it? So what if I had a component that was in the negative I hat direction, and I want to take the cross product of it with something that's in the positive j hat direction? Well, algebraically, the only thing that's happened is we've multiplied our I hat component by a -1. And we already know what happens when we get I hat cross j hat. We get a positive k hat. But now, waiting out front is a -1. And what is that -1 going to do to our positive k? Well, it's going to turn it into a negative k hat. And that is purely a result of the algebra. And so what would happen if you had two negatives? What would that result in? Well, again, we've got a -1 times our I hat. We've got a -1 times our j hat. And we already know what I hat j hat equals. It's positive k hat. But then there's two -1s that have to be multiplied against that, but two negatives makes a positive, and so there we have it. Let's try one more. Let's try negative I hat cross negative k hat. Now in this case, if you really wanted to, you could factor out those -1s right away. And the moment you do that, you realize, well, two negatives makes a positive. All that's left is I cross k. But I cross k, that goes against the alphabet. And so we get a -j as a result. And we should know that because we've already seen that example before. So if you do have any minus signs attached to your components, don't worry about it. Just carry those along algebraically and you'll be fine. Case in point, let's go back up here. For AX cross BY, we know that our value of 21 is going to be in the k hat direction, but is it positive or negative? Well, AX is I hat, BY is j hat. I cross j equals what? Positive or negative k? Well, we're going with the alphabet, so that's a positive k hat. Positive k hat. So 21 positive k hat. That's what we get for AX cross BY. And now that we can see how everything fits together, going through the other combinations should go pretty quick. AX cross BZ. So we need the magnitude of AX, which is 3. We need the magnitude of BZ. And oops, I made an error on the previous evaluation. I don't know if anybody caught that. AX cross BY. If we look back up here, BY was a -7 j hat. And I used the magnitude of 7 here, so where does the minus sign go? Well, that minus sign has to go with the j hat. So, my bad. We're actually going to get a minus k hat out of that. Oops. My eraser function is not wanting to work well. There we go. Negative k hat. back to AX cross BZ. Okay, AX had a magnitude of 3, BZ has a magnitude of 2. The sine of the angle between them, the angle is 90 degrees, so we're getting a magnitude of 6. I'm using I hat cross K hat, so I know I have to have a J hat, but is it positive or negative? And looking back at our function, we had positive J hat, positive K hat for our components. So positive I hat cross positive J hat equals, that's going against the alphabet, that's a negative J hat. AY cross BX. So AY has a magnitude of 5. BX has a magnitude of 4. Both of those were positive components. We get another sine of 90, so we have 20. Positive J hat cross positive I hat equals, we're going against the alphabet, and that is a minus K hat. We got 0 from that combination. AY, magnitude 4. BZ is magnitude 2. Sine of 90. So we have a magnitude of 8. J hat cross K hat. Both components were positive. So positive J hat cross positive K hat. That does go with the alphabet, so we get a positive I hat as a result from that. And last line of the matrix here, AZ cross BX. So AZ, magnitude 8. BX, magnitude 4. 90 degrees between those components. So we have magnitude 32. Both of the components were positive, so we have positive K hat cross positive I hat. K hat cross I hat, that does go with the alphabet. We're starting at K, and we have to start over with the song. So K cross I equals positive J. And then AZ cross BY. AZ, magnitude 8. BY, magnitude 7. Magnitude 7. Sine of 90. 8 and 7, what is that, 56 magnitude? Sorry, I should have been pairing that with this one. I'll just write that down here again. 7 sine 90 is 56. And we have K hat crossed with B of Y. B of Y was a negative, so we have a negative J hat. Now, K hat cross J hat, that goes against the alphabet, so technically that's a negative I, but we have the negative attached to the J hat, so it becomes a positive I. Now, why are we being so critical about the I hat, J hat outcome? Well, because now I have 6 different values on the page which need to be combined based on their term. I have 2 terms that are going to end up contributing to the final z component of our vector. I have two terms that are going to contribute to the final y component, and I have two terms that are going to contribute to the final x component. And so the way we do that is, well, we're going to add them together. We have taken our two vectors, a and b, and we said that a cross b results in a new vector that we call c, and vector c is going to have three components, I, j, and k. So the x component of vector c can be found by combining the I hat results from all of our cross products. And we have a 56 positive I hat and an 8 positive I hat, which will result in, what is that, positive 64. Y component of vector c will be the combination of the j hats. We have a positive 32, a negative 6. So 32 minus 6. And what is that going to be? 26. Positive j hat. And the z component will be the combination of the k hats, which are both negative. Negative 21 and a negative 20 makes for a negative 41. And so there's vector c. Vector c has components of 64 I hat plus 26 j hat minus 41 k hat. And even though this looks like a really drawn out way of evaluating a vector, there's one really good outcome to this. And if you remember, we tried evaluating this using the angle relationship between vectors a and b, and we said, well, we have no idea what the vector is between those two. Or we have no idea of what that angle is between those two vectors. Well, now we don't have to know, because vector c is a three-dimensional vector out in space, and by the rules of cross products, this vector has to be perpendicular to the original two. And there are methods in linear algebra and Calc 3 that you can use to actually prove this. But that's not something that we're going to be doing in today's video. All right, well, given where we're at right now, this looks like a huge mess. And so is there some way that we could put all of this stuff together in a general expression that we can use for any combination of vector components that are going to be crossed together? And there is. If we go back and kind of look at the pattern of things that have occurred here, we had AX cross BY, which resulted in a K hat, and we had an AY cross BX, J hat cross I hat, that resulted in a negative K hat. Now I'm not including the fact that some of these components were positive or negative. But what's happening here is that just by switching around the order of the components, we get a change in the sign for the outcome. And so what we have here is when we go through and we evaluate this, the only thing that was left over in the evaluation were the values of ax and by. And then we had the values of ay and bx with the negative k hat. Well, let's take that minus sign. We'll move it out to the front here. And now what we have is a general expression that takes all of those x and y components that have been crossed together, and it tells us what the final z component of our resultant vector needs to be. Likewise, we can do the same thing with ay bz minus az by, and these are the j and k's, and so these will result in the I hat component of our final vector. And again, you can go back to this mess of a system that we have here, but you can see pretty easily that having our two combinations of cross products here, again, not factoring in the fact that any of these are positive or negative components, those values can actually be plugged in here. This method does not require that we use the magnitude of the components. We can just leave them in there. And then the last combination would be, let's see, we need az bx minus ax bz, and that would tell us what the j hat components of our final vector are. So if A cross B equals C, the way that we get the components for vector C, so vector C has components I, j, k. Now we have our expressions. Now we have exactly what we need to plug in for any general system of vectors. Our j hat right there, az bx minus ax bz, and then our k hat is ax by minus ay bx. All right. So from now on, we can just start right here. We can use this equation to evaluate any cross product that we're given, and we don't have to go through this method of evaluating all 9 possible combinations of these vectors, because we've already done that right here. And we've seen what happens when we combine these vector components in the given fashions. We don't have to come back and redo the derivation of this expression. It's ready to go. And so now we can take this idea into chapter 28, which talks about the magnetic force that acts on a charged particle. That magnetic force will have x, y, and z components potentially, if it is a 3D system. And the components of that force are going to equal the scalar charge value times the cross product of vector v and vector b. And so we would use this method on the components of our velocity vector and our field vector, keeping in mind that all of our answers have to be multiplied by the scalar value of q, and that will give us all of the vector components of our magnetic force. We can then take the same idea into chapter 29, which talks about force vector on a wire that is sitting within a magnetic field, and that wire has length of L. The current running through the wire is I. Again, I is a scalar, just like Q was a scalar. And our force vector could, again, potentially have XYZ components. And we would find those components, I is the current here. But we would take the scalar value of the current times the cross product evaluation that we get from the direction in which the wire is pointing versus the direction that the magnetic field is pointing. Now typically these kinds of problems are a lot easier because you have a wire that is carrying current in a given direction, and you know where your magnetic field is pointing. And so if you don't want to go this route with evaluating your cross product, remember that there's always the easy way. If you have two vectors and you know what the angle relationship is between them, I mean, just look at this wire. L is pointing up, field is pointing into the board. That's a 90-degree relationship. Why would you ever want to go through this if you know what your angle relationship is? Because then it's just a matter of taking the magnitudes of each, so the length of the wire times the magnitude of your magnetic field times your current, and you're done. In this case, the only direction that we can have for our magnetic force would be to the left or the right. But now we can actually figure this out. If L, let's see here, let's put in our right hand reference frame. So we have X coming out of the board, we have Y going left and right, we have Z going up and down. L is in the Z direction, so that's K hat. B is going into the page, so that is technically the negative I hat direction. We have K hat cross negative I hat. Factor the negative 1 out if you want. K hat cross I hat. What do we get? And I am not going to go back up to the top of the page where we had all of our cross product combinations, because at this point we should be able to tell if we're going with or against the alphabet here. K cross I. So does I come after K in the alphabet song? We're starting at K and we have to go to I. Yep, we're going with the alphabet, so this is a positive J hat. We got the minus sign out front, so that turns it into a negative J hat, which means that the resulting force on this wire needs to be pointing in the negative J hat direction. If you prefer to use your right hand rule, you can also do that. Right hand rule says the first vector in your evaluation is your index finger. So you have to point your index finger in the k-hat direction. Second vector is your middle finger. So you need to point your middle finger into the page. The result is your thumb. So which way does your thumb point if your index finger is up, middle finger is into the page? Well, your thumb has to point in that direction. So now we know everything that we need to know to evaluate any kind of cross product. And again, this is why I went for the full three-dimensional system, because now if we do end up reducing this down to a system of 2D vectors or 1D vectors, the math is only going to become easier for us. But this equation can still work for a system of 2D vectors or 1D vectors. 2D vectors only have two components. So what would you do if vectors A and B only had x and y components? Well, that means that you would have to set all your z components to 0. We get a 0 there, we get a 0 there, we get a 0 there. Any other zeros? There's a 0. So for vectors A and B that were all in the x and y directions, we only got an outcome for the k-hat, which, well, that's exactly what we should have expected. Alright, that brings us to the end of this video. So go back, check your work in chapters 28 and 29. If you do have any 3D vectors that need to be crossed, we now have our method of doing that. As a little side exercise, I might ask you to see if you can figure out what the angle is between vectors A and B. We very easily could have evaluated this system if we had just known what theta was. Well, you know what the evaluation of this vector is now. It's the combination of everything that we got from this equation. So with vector C having x, y, z components, can you tell me the magnitude of vector C? And if so, can you tell me what that missing angle is? See you at the next video.